guys. Today we're going to look at two-dimensional kinematics. Okay, we've been doing this stuff where we shoot an object straight up in the air, it comes down. We've been doing this stuff where we're going straight along a line like a car or a ball or something going back and forth. Now we're going to be looking at things that go through two-dimensional space, so not just a straight line. So we're going to be looking at shooting a basketball, right? Shooting a basketball has this parabolic shape. We're going to be looking at throwing things off of a cliff where not only does it fly straight, but it also falls as it flies. Okay, it's going to be really important that we tie in the idea of vectors that we've been talking about for the last couple of weeks. Talked about the fact that vertical and horizontal pieces, the up and down and the horizontal, are independent of each other. They're not going to affect each other. This is going to be a really important idea as we start to look at two-dimensional kinematics, because otherwise it gets very, very confusing when you have acceleration, gravity is pulling something down, but then horizontally it's not accelerating. Okay, so it can get very confusing very quickly if we don't break it up. And this is why it was so important that we learned how to take a vector and split it up into its components. So we're going to use that today as we work on these couple of problems. So I'm going to do one in this video, and then I'll do another video and maybe another one later. We'll just see what kind of happens. All right, so here's the first question. Mr. Bywater wants to bomb the biology teacher's house with bananas. Yep, sounds like me. He has a drone that can fly at 50 meters a second with a height of 100 meters. How far before her house should the drone release the bananas? Okay, so picture, I'm not an amazing artist, but here we go. Here's my drone. Drone's carrying bananas. There's bananas. Yes, they're black. That's because they're very, very ripe, and that way they make a bigger mess when they land on the biology teacher's house. So my drone carrying the bananas can go at 50 meters per second. It is 100 meters up in the air. Here's the ground, and then the biology teacher's house is over here. Give it a couple of windows and a frowny face because it knows there's a biology teacher living inside. So anyway, it'll probably be happier once it's bombed with bananas. Anyway, here we go. This is the problem. The question is, as I'm flying, when do I need to release those bananas so that I can release it, do my hit and run, my drone can just keep on flying. Okay, recognize that right now the bananas are flying at the same speed as the drone. The bananas have a horizontal speed of 50 meters a second, so therefore they're moving. When I release them, they're going to continue moving this direction, and yet gravity is going to start pulling them down, so they're going to follow kind of a parabolic motion. So the question, of course, is at which position, how far before the house should I release those bananas? We can do that. We can do that with the knowledge that we have now using our kinematics equations, all right? So that's what we're going to do. So the first thing that we have to do, just like any other kinematics equation, is we're going to list out the information that we have. Now, because this is two-dimensional with the up and down and the side to side, we're going to have an extra column, all right? We're going to have an extra column in our SUVAT. So normally we have SUVAT, and then we have just the one column of information. Here we're going to have two sets of data. We're going to have our X, which is the horizontal information, what's happening horizontally, and then I'm going to have Y, which is the vertical information, what's happening vertically. Remember, these are independent of each other. They don't affect each other, therefore we can work with both. All right? So, X displacement. Now remember, the beginning is here, the ending is here. So my horizontal displacement is just how far horizontally it's going to be displaced between the beginning and the end. So that's this distance right here. That is what I'm actually looking for, right? That's the distance that I want. So this is what I want right there. So I'm going to put an S right there for displacement. Okay, now I'm going to move on to the initial velocity. What is the initial velocity horizontally of the bananas? Well, the bananas are traveling at 50 meters a second to the right, so that's a positive 50 meters per second. So I'm going to go 50 meters per second. Now, we're going to assume, as we do in many introductory physics questions, that there's no air friction, okay? Just because that adds in another factor of difficulty. So we're going to say no air friction. So if there's no air friction, okay, we now need the final velocity, the horizontal velocity. We're not even looking at what happens as it falls. We're just saying what happens horizontally. Well, maybe it's more important to first look at the horizontal acceleration. As I drop the bananas, is there anything causing the bananas to accelerate horizontally? Is there anything pushing on it to speed it up or pushing on it to slow it down? The answer is no. Horizontally, there is nothing causing it to change its speed. There's no extra forces. We're going to talk more about forces in our next part of this unit. Okay, but our acceleration is 0, so our velocity, our final velocity horizontally is the same. Okay, it's exactly the same. It's 50 meters per second. Now the time, I don't know how long it's going to take to get from here to here because I don't know the distance, of course. So now we're going to move on to the vertical information. What do we have vertically? Okay, so vertically, what will my displacement be? Well, it's starting up here, and it's going to end down here at the ground. So what is the vertical displacement? It's 100 meters, right? So we're going to put 100 meters in for the displacement. And because it's down, I'm going to put a negative in. All right? Moving on. The initial velocity vertically. When it's released, it's not moving up or down, right? At that instant of release, it has an initial velocity of 0. All right? Of course, as it falls, it's going to speed up because gravity's pulling down, just like it pulled down on my marker right there. But the idea is the initial velocity is 0 meters per second. Final velocity, I don't know how fast it's going to go when it hit by the time it hits the house, so I'm going to skip that for now. Acceleration. Acceleration vertically is caused by gravity, so we've got our acceleration of negative 9.81 meters per second. For our purposes right now, I'm going to use a negative 10. I wanted to put that up there to remind you that's what you'll use because you got a calculator. To simplify, I'm just going to do negative 10 meters per second squared as my acceleration. Okay, moving on. Time, again, I don't know anything about time. So now I have all of my information there, right? Everything that I need is right there. The question now is, how do I get the information what I want? I want this S right here. Well, do I have an equation that allows me to use U, V, and A to solve for S? Something that doesn't have T in it. Okay, well, let's look. This has T, so I don't want that. This has T, so I don't want that. This has T. So I've got this one, which has V, U, A, and S, but you'll notice that if acceleration is 0, what happens to my displacement? It gets multiplied by 0, it goes away. So I won't be able to use that one this time. So what would be really helpful is if I could find the time. Now I won't be able to get the time from my horizontal information, but given that I have vertical information, I can get the time there. And those two times are going to have to be the same. Because what that is that's the time it takes me to travel that distance and the time it takes me to fall this distance. And since my bananas are going like this, to right there, then the time it takes me to fall 100 meters is the same as the time it takes me to travel horizontally that distance. Okay? So what we're going to do is we're going to use SUVAT on the Y first, and then we'll work from there. So I've got S, U, A, and I want T. So I don't have final velocity. So let's take out the ones with final velocity. So I don't want this one. That one looks promising. This has V, this has V. So that's the one I want right there. S equals UT plus 1/2 AT squared. So S equals UT plus 1/2 AT squared. Go ahead and put the numbers in. So I've got S, which was negative 100, equals the initial velocity, which was U for Y. I'm doing the vertical stuff here. If you want, make this an SY to show you that that's the vertical information. Or right up above, this is vertical. Okay? Do something so that the reader understands, whoever's grading your paper knows what you're talking about. And also for you, because if you come back to this question later, you want to be able to go through your process and say, yep, this is what I did, this is what I did, this is what I did. So make sure you label this somehow either as the vertical displacement, therefore the vertical velocity, all these other things, or just up at the top say, hey, this is vertical. Okay, so I'm dealing with the vertical stuff. Negative 100 equals U, which was 0, so that's actually going to go away, plus 1/2 times acceleration, which was negative 10, times T squared. All right, at this point, you should be able to work that out. We're going to have negative 100 equals -5 times t squared divided by the -5, and I get 20 equals t squared. Go ahead and put that in. And we got the square root of 20. And I got 4.47, so I'm going to put that in. So t equals 4.47 seconds. So that's my time. Okay, now this is not the end of the question. This is how long before I get there do I need to release it, 4.47 seconds. But if I'm looking for distance, then now I need to apply that to the horizontal material. So that's what I'm going to do in my last step here. So I've done my vertical. This is now 4.47. So I'm going to put that here. So now I have the information that I need to get S, and I can choose any of my equations over there as long as they have an S in them. Okay, I'm going to choose this one because this looks like it's probably going to be the easiest one because S is already by itself. So for my final little bit, I'm going to say S equals V, which was 50, plus U, which was 50, right? Times the time, which was 4.47, all over 2. I'm going to go ahead and punch that in. You do it on your own. So 100 times 4, I'm going to go ahead and say to do the answer. Always when you can, use the whole previous number. You'll see on my calculator right here, I've had it do 100 times the answer, because that's going to give me all the digits of that 4.47 there. So there we go, for 100 times the answer, and then I'll divide by 2, which of course will give me my answer, which is 223.6 meters. So the answer to the question is, how far before a house should the drone release the bananas? 223.6 meters. Okay. Now, how can we take this further? What's another question that could be asked? Another question that's very commonly asked would be something like this, to say, all right, well, you've done a great job finding all this information. How about this? With what speed will the bananas strike the house? Okay, now this is a slightly different question, right? Because we have this stuff right here, right? Where we know the horizontal stuff, we know the vertical stuff, but how are the bananas actually striking the house? Are they just hitting it horizontally? Nope. Are they just landing straight down vertically? Nope. Right? We know that they're going to come down kind of at an angle. All right? This is where that vector stuff, in addition to recognizing that we can separate the horizontal and vertical, this is where that vector stuff is going to come into play. Because we recognize that we can take the horizontal and vertical pieces and put them together. Okay? So if I want to know the speed with which they strike the house, then I need to know the final vertical velocity, and I need to know the final horizontal velocity. If I have both of those, I can put them back together again, because we learned how to do that with vectors, and velocity is a vector, and I can get the final velocity, or the final speed. So I need, what do I need? I need this now. I need to know the final velocity in the y direction. What's happening as it's falling, as it's speeding up? Okay, well, looks like I'm going to need to use some other information. Which equation? I can use pretty much any of them. I think I'm going to go with this one right here. The reason why is because v is by itself. It's not squared or anything else. So I'm going to try that one first. So I'm going to go v equals u plus at. So v is what I'm looking for, equals u, initial velocity was 0, plus the acceleration, which is negative 9.81, times the time, which was, of course, 4.47 seconds. Sorry, I was not using 9.81 here. I was using 10 so that it would be simpler. So my velocity as it hits the house is negative 44.7 meters per second, right? So now I have a vertical velocity. That wasn't necessary for the first part of the question, but if I go here, negative 44.7 meters per second.
Mr. Bow, what did that mean? Negative 44 meters per second.
What does that mean? Why is there a negative there? Hopefully you got it. Hopefully you remember that negative is talking about the direction, right? And so that means that it's traveling downwards, which we already knew. But it should match up. If you get a positive here, there's a problem, because that means that you have my bananas going upwards after I drop them, which, yeah, that's a problem. Okay, so we've got that speed. So now how do we get the final speed? Well, to get the final speed, you take the two vectors and you put them together, okay? So we're going to take the horizontal vector. Horizontally, we know its final velocity is 50 meters per second. Vertically, the velocity is negative 44.7, head to tail. So we put those together to get our resultant vector here. Notice that because it's horizontal and vertical, it's a right angle. So we just use Pythagorean theorem. So we're going to go 50 squared plus 44.7 squared. Of course, you should use your answer there, right? Use the previous answer of the 4.47 times 10. Use the full digits as long as you can. And then you're going to square root it. And you should get something around 67. Maybe 67.1, something around there. So about 67.1 meters per second. And that is the speed at which the bananas will hit the house. You could, of course, find the direction as well, right? You could find out exactly what angle it's going to hit by using your trig here. You could use opposite over adjacent. Use your tangent to find out the angle at which it hits the house as well. Okay? So all of these things that we've learned, they can come into play. I can't possibly cover every single one of those in a video. It would take me weeks to make all the videos to do that. You have to learn these principles and be able to apply them and combine them with other ideas to fit other situations. All right? So there you go. That's example number 1. Watch example number 2 in just a minute, where we're going to do something slightly more complex. Until next time.